This is a spark plug, $5, a piece of metal and ceramic that you probably think about once every few years. But right now, one incredibly common mistake with this exact part is quietly removing 100,000 miles from the life of engines all over the world. You will not see a check engine light when it starts. Your mechanic probably will not catch it during a routine oil change. The only warning you might get is a split-second hesitation when you step on the gas. But that stutter is the start of a chain reaction that will eventually force you to replace your entire engine. I spent weeks going through mechanic forums, Reddit threads, and technician case studies. I found 13 distinct mistakes. Some contradict things you have believed your entire driving life. This is a countdown, 13 down to 1. And the number one mistake is something almost every car owner has done at least once, without realizing it was accelerating damage in every cylinder they never touched. Around mistake number 8, I am also going to explain something called LSPI, low-speed pre-ignition. If you drive a turbocharged car made in the last 10 years, remember that term. You pull a spark plug out of your engine. The electrode is there, nothing is cracked, nothing is melted, it looks fine. But run your eyes along the white ceramic insulator. See that faint dark trail? That is carbon tracking. And that trail just turned your spark plug into an expensive piece of metal that is no longer doing its job. That is mistake number 13, leaving your plugs in service too long. Over thousands of miles, conductive carbon deposits creep along the ceramic insulator. Once that trail connects, ignition energy stops jumping across the electrode gap. Instead, it travels along that carbon trail straight to ground. The engine still runs, it just runs worse. Misfires here and there, a little roughness under load. Most people blame the coils, the wires, the fuel injectors. They throw parts at it for months. And the whole time, the answer was sitting in the plug well, looking perfectly innocent. This connects to something we will come back to later. If you do a lot of short trips where the engine never fully warms up, or extended idling, your plugs never reach the temperatures they need to burn off those carbon deposits. Toyota 2AZ engine owners documented plugs fouling in just a few thousand miles under those conditions. That buildup is exactly how "it is still running fine" turns into "why is my engine misfiring under load?" And the cascading damage does not stop at the plug. It climbs right into your ignition coils. $5 for a spark plug, $300 for a coil, $1,000 by the time you are done chasing symptoms, all because of a service interval that got ignored. The next mistake is something you are probably doing every single time you change your plugs, and you think you are doing it right. You can apply the exact correct torque to a spark plug and still crack it in half. The reading on your wrench is perfect, and the plug shatters anyway. How? That is mistake number 12. Using the wrong installation tools. Impact wrenches deliver torque in short, violent bursts that last only milliseconds. The ceramic insulator needs smooth, steady rotation, not rapid shock loads that crack the porcelain. Sometimes as a hairline fracture you cannot even see, sometimes as a full split that leaves threaded shell pieces stuck in the head. The second tool that causes this might surprise you. The rubber insert spark plug socket. It grips the porcelain insulator to hold the plug in place. Sounds helpful, except the rubber pushes sideways against the ceramic instead of providing pure straight down rotation. That sideways force can crack porcelain even when your torque is completely within spec. Remember that term, hairline fracture. We are going to come back to it at mistake number 5. And when we do, it is going to explain one of the most frustrating diagnostic nightmares in automotive repair. The fix is specific: sockets without rubber inserts. An inch-pound torque wrench because spark plug torque specs are often in a range where standard foot-pound wrenches lack precision. The torque number on your wrench means nothing if the tool delivering it is destroying the part from the inside. You pull a spark plug, you look at the color. Black means too rich, white means too lean, oily means bad rings. Problem solved, right? Not even close. That is mistake number 11, misreading spark plug diagnostics. Spark plug color is a clue, not a verdict. Treating it like one is how people spend hundreds replacing plugs while the real problem gets worse with every mile. Grayish tan means healthy combustion. Black soot usually means carbon fouling from a rich mixture. Oily deposits suggest worn piston rings or valve seals. White or ashy buildup can point to oil additives or fuel chemistry issues. Blistered or melted electrodes signal overheating. But arcing from worn-out coil boots or spark plug wires can create misfires that look exactly like porcelain damage. In waste spark systems, that arcing stress doubles. The proper diagnostic sequence goes like this. OBD2, scan first. Pull suspect plugs and inspect. Then swap ignition coils between cylinders. If the misfire follows a specific coil, that coil is the problem. If it stays in the same cylinder, you need compression testing, leak down testing, and fuel pressure checks. Honda Civic owners documented this progression perfectly. Some found misfires tracing back to old coils or degraded wiring. Easy fix once they stopped blaming the plugs. Others found coolant on electrodes, white deposits, and a sweet odor, which led to head gasket testing. Mistake number 10. Skipping hand threading. The first 3 turns determine everything. When you thread a spark plug into an aluminum cylinder head, those rotations by hand are your only chance to confirm the threads are following the path that already exists in the head. Skip them, go straight to a socket, and you risk cutting a brand new path through softer aluminum. That is cross-threading, and it does not always fight you. Sometimes the plug seats and appears to torque correctly, but underneath, the misaligned threads have weakened the aluminum. Over thousands of heat cycles, that weakened engagement loosens until combustion pressure ejects the plug entirely. Blowouts in aluminum heads are permanent damage without a repair insert. Hand starting every plug costs you 30 seconds. Skipping it can cost you a cylinder head. But what if the plug itself is the wrong physical size for your engine? What if it threads in perfectly, seats properly, torques to spec, and then the piston hits it? That is mistake number 9, wrong spark plug reach or seat type. You install a spark plug. Everything feels correct. You start the engine. And on every compression stroke, the piston crown collides with the plug tip because the threaded portion extends too far into the combustion chamber. Electrodes bent completely sideways. Piston crowns with deep gouges. Engines that sounded like they had valve train problems. And it all started because the plug fit the threads but had the wrong reach. This mistake is almost always introduced by parts counter substitutions. The thread pitch matches, the diameter is correct, but the reach is wrong or the sealing method is wrong. Some engines use a gasket seat, others use a tapered seat. Mix those up and you change the sealing geometry and heat transfer path entirely. Before you install any spark plug, verify the reach and seat type against your specific engine. Not the thread diameter, not the pitch. If it does not match, it does not belong in your engine. Mistake number 8. Ignoring early pre-ignition or knock symptoms. You hear a faint metallic ticking under load, maybe some power loss that comes and goes. The check engine light flickers for a second, then disappears, and you keep driving. The timeline is always the same. Stage 1, subtle electrode erosion. Stage 2, electrode melting. Stage 3, piston crown damage. Stage 4, catastrophic failure. Ring land cracking. Piston holing. An engine that was completely savable at stage 1 for $100 is a $5,000 rebuild at stage 4. All because someone kept driving. Knock sensors do not always catch every pre-ignition event. Sensor faults or factory tuning strategies can mask it entirely, so your car's computer might not even know it is happening. Now, remember LSPI from the beginning? Low speed pre-ignition. This is where it becomes real. Something alarming is showing up in small displacement turbocharged direct injection engines. These are not exotic cars. These are the engines in your Civic, your Mazda 3, your Ford Escape. LSPI events are being documented with ground straps ripped off, electrodes melted, pistons cracked. And it happens specifically at low RPM under high load, the exact conditions you create every time you lug the engine up a hill without downshifting. The causes are modern engineering compromises. Carbon buildup on intake valves forming hotspots. Oil chemistry interacting with combustion deposits. Aggressive factory lean calibrations designed to squeeze out better fuel economy. And this is why I told you to remember LSPI. It connects to mistake number 13 because short trips increase carbon deposits that create hotspots. It connects to mistake number 6 because the wrong heat range plug cannot dissipate heat fast enough. And it connects directly to this mistake because the early symptoms, that faint ticking, that momentary power loss, are your only warning before the piston cracks. The mitigation is practical. More frequent oil changes with manufacturer-specified oil. Intake valve cleaning like walnut blasting. Avoid lugging the engine under heavy load at low RPMs. Periodically drive at higher RPMs to burn off deposits. Those early symptoms are a gift. The owners who acted on the first ping saved their engines. The owners who waited were already past the point of affordable repair. Mistake number 7, incorrect spark plug gap. When was the last time you actually measured the gap on a spark plug before you installed it? If you are like most people, never. You assumed it came pre-gapped from the factory, and for most standard applications, it does. But that assumption starts costing money the moment conditions change. That tiny airspace between the center electrode and the ground electrode controls how much energy the spark carries into the fuel-air mixture. Too narrow and combustion is weak. Too wide and the ignition system cannot push enough voltage across. Misfires under boost, at high RPM or in cold starts. Gaps change over time. Electrodes erode with every spark event. A spark plug perfectly gapped at 30,000 miles might be significantly out of spec by 60,000. And the symptoms, intermittent misfires, rough cold starts, hesitation under load, look exactly like a dozen other problems. In forced induction engines, higher cylinder pressures make it even harder for the spark to jump. Owners running boost commonly close the gap from stock specifications to prevent misfires under load. Use wire-type feeler gauges for round electrodes. When adjusting, only bend the ground electrode. Never touch the center electrode. Bending the center electrode can crack the insulator, which circles right back to that hairline fracture problem from mistake number 12. Check the gap with the right tool. Verify against your specific engine specification. The spark plug gap controls ignition energy. But the other half of what happens at the plug tip is thermal, and getting the thermal side wrong melts your pistons. Mistake number 6, wrong heat range selection. Heat range is how quickly the spark plug transfers heat from the combustion chamber to the cylinder head. A hot spark plug transfers heat slowly, retains more heat. A cold plug transfers heat quickly, stays cooler. The spark plug tip needs to stay in a specific temperature window. Above roughly 450 degrees Celsius, it burns off carbon deposits. That is the self-cleaning threshold. Below roughly 850 degrees, it stays cool enough that it does not become a secondary ignition source. Go below the self-cleaning threshold and deposits build up. The spark plug fouls. Go above the upper limit and the plug tip ignites fuel before the spark fires. That is pre-ignition. Uncontrolled pre-ignition destroys pistons. The manufacturer picks a heat range for your specific engine based on compression ratio, cooling system design, fuel type, and expected driving patterns. People change the heat range without understanding what they are changing. They put a hotter spark plug in a high-performance engine because someone on a forum said it prevents fouling. Under sustained high RPM or boost, it becomes a glowing ignition source. Pre-ignition, piston damage. Or they put a colder plug in a daily driver that does short trips. The spark plug never reaches self-cleaning temperature. Carbon builds up. And now you have created mistake number 13 all over again, but faster. The numbering systems make this worse. In NGK plugs, a higher number means hotter. In Denso, a higher number means colder. Champion uses a completely different system. Cross-referencing between brands without understanding this inversion is how people accidentally install a spark plug 2 or 3 heat ranges off. Now, remember back at mistake number 12, I mentioned hairline fractures? Those of you who have been paying attention know exactly where this is going. Mistake number 5, pre-installation damage from dropping or mishandling plugs. You open a new spark plug, it slips out of your fingers. Bounces once on the concrete floor, no visible cracks, no chips. Electrode looks fine, so you install it. That plug now has an invisible fracture inside the ceramic. Under extreme heat and pressure, that crack propagates. As it opens, it creates a new path for spark energy to escape. Instead of jumping the electrode gap, the energy leaks through the crack. The plug fires perfectly cold. Once the engine reaches operating temperature and the ceramic expands, the crack opens. Misfire. Let the engine cool, the crack closes, plug fires fine again. Imagine trying to diagnose that. You pull the spark plug, it looks perfect. You test it outside the engine, it sparks fine. You swap coils, same misfire. You swap injectors, same misfire. And the whole time it was a microscopic crack from a 2-foot drop onto a garage floor. If you drop a spark plug, replace it. A $4 spark plug is not worth weeks of diagnostic confusion. Handle them like they are made of glass, because functionally, they are. But what happens when a spark plug does shatter inside your engine? When a shell gets stuck in the threads, or the porcelain breaks off into the combustion chamber? Mistake number 4. Improper or forced repair procedures. This is the mistake that turns a bad situation into a catastrophic one. It usually starts with a stuck spark plug, seized in the head from corrosion between dissimilar metals. You put a socket on it, it does not move, so you pull harder. The plug twists, but the shell stays. Or the porcelain shatters. Or the threads strip out of the aluminum head. Porcelain fragments scoring cylinder walls, shell pieces wedged in threads. Ford Triton 5.4-liter V8 owners know this problem better than anyone. The two-piece spark plug design on those engines is notorious for shell separation during removal. An entire category of aftermarket extraction tools exists specifically for this engine. Prevention starts with penetrating oil the day before removal. Heat cycles by warming the engine and letting it cool. Slow, steady rotation. If resistance increases sharply, stop. Apply more penetrant. Try again after another heat cycle. If the spark plug has already broken, debris control is the absolute first priority. Compressed air to blow fragments away from the combustion chamber. Grease on extraction tools to catch ceramic particles. Bore scope inspection to verify the cylinder is clear before starting the engine. The line between a successful extraction and a destroyed cylinder head is measured in patience. Mistake number 3. Counterfeit or unreliable spark plug sourcing. There is an entire industry of counterfeit spark plugs. Fake NGK, fake Denso, fake Bosch. Packaging that looks identical. Part numbers that match. And inside, a plug manufactured with no quality control and no performance testing. Counterfeit plugs with off-center electrodes and inconsistent porcelain density. Ground electrodes made from base metal instead of the nickel alloy specified for the genuine part. Thread quality so poor that cross-threading becomes almost guaranteed. And the most dangerous part is that they work, at least for a while, long enough for the damage to begin. The sourcing risk is concentrated in third-party online sellers with low feedback counts, swap meets, and discount parts bins at non-franchise retailers. Buy only from authorized distributors or directly from the brand's website. For NGK, check the logo shape and uniform ceramic color. For Denso, verify the laser-etched markings. For Bosch, check the holographic seal against their online verification tool. You can do everything else on this list correctly. Perfect gap, perfect torque, perfect heat range. A counterfeit plug will still fail. A genuine plug costs $4 to $12. Mistake number 2. The anti-seize debate. Should you put anti-seize compound on spark plug threads before installation? Ask 10 mechanics and you will get 10 different answers. The Always Use It camp says anti-seize prevents galvanic corrosion between the steel spark plug shell and the aluminum cylinder head. Without it, over thousands of heat cycles, the dissimilar metals bond together. Removal becomes a nightmare. We just talked about this at mistake number 4. The Never Use It camp has an equally strong case. Most spark plug manufacturers, including NGK and Denso, state that their spark plugs come with zinc or nickel plating that already serves as a corrosion barrier. When you add anti-seize on top of that plating, you change the friction coefficient. Torque specifications are calibrated for dry threads or the factory coating. Anti-seize reduces friction, so when your torque wrench clicks at the specified value, the actual clamping force is higher than intended. You are over-torquing without knowing it. Long-term owners of aluminum head engines in corrosive environments report that anti-seize saved them from catastrophic removal problems. On the other side, owners who used anti-seize and torqued to factory spec reported cracked insulators from overcompression. If the manufacturer says do not use anti-seize, follow that instruction. If you choose to use it anyway, reduce the torque value by 10 to 20% to compensate. Some recommend applying only a thin smear to the first 2 threads, avoiding the sealing surface entirely. If you are not accounting for what you put on those threads, you are not actually torquing to spec even though your wrench says you are. Mistake number 1, the panic crank. You are extracting an old seized spark plug. You apply a little too much force to the ratchet and suddenly it goes loose. But the threads did not turn. The spark plug snapped in half. The hex nut and the top half of the ceramic insulator are in your socket, but the threaded shell and the bottom of the ceramic are still stuck in the cylinder head, and shards of that broken ceramic have fallen down into the spark plug tube. At this exact moment, human psychology takes over. Pure panic sets in. You do not want to tow the car to a machine shop. You do not want to take the cylinder head off. You just want the ceramic out. So someone on a forum, or that little voice in your head, gives you the worst advice in the automotive world. Just crank the engine. The compression will shoot the ceramic pieces out of the spark plug hole. You turn the key. The engine cranks. And you just destroyed your engine block in 3 seconds. Spark plug ceramic is aluminum oxide. It is harder than steel. It is harder than your engine block. When the piston comes up on the exhaust stroke, those ceramic shards do not gracefully exit the spark plug hole. They get caught between the aluminum piston skirt and the steel cylinder wall. As the starter motor forces that piston up and down, those ceramic shards act like diamonds carving glass. They gouge deep, irreparable trenches into the cylinder wall. A $300 mobile extraction job has just become a $5,000 total engine replacement. When a spark plug breaks and debris is in the hole, you stop. You step away, you use a bore scope and a specialized micro vacuum, but you never ever turn that key. So let me bring this full circle. Every single one of these 13 mistakes comes down to the same fatal assumption, that a spark plug is just a piece of metal you screw into a hole until it feels tight. It is not. It is the most critical diagnostic window your engine has, and it demands precision at every single step. But here's the thing, even if you do all of this perfectly, your engine can still misfire, because spark plugs are only half the ignition story. There is another component sitting right next to every plug you just installed, and when it silently fails, 99% of drivers find out way too late. That video is on your screen right now. I will see you there.